All right, today we are going to decode a language that's literally all around us. It's not English, it's not code, but it describes every single thing you can see and touch. So let's just dive right in. So you see stuff like this all the time, right? H2O, NaC. They look kind of like a secret code, don't they? Well, in a way they are. But here's the thing. By the end of this, you're not just going to be able to read this language. Nope. You're going to learn how to write it yourself. Ready to get fluent? You know, just like any language you might learn, chemistry has its own alphabet and its own grammar. And once you get a handle on those two things, the whole world of matter just opens up. Let's decode it together. What's so amazing about this language is how precise it is. I mean, you can say the word water, and that could mean a lot of things. But when a chemist writes H2O, whoa, that's super specific. It means exactly 2 hydrogen atoms and 1 oxygen atom. There's just no room for confusion. It's a language with zero ambiguity. So where do we start with any language? With the alphabet, right? Well, in chemistry, our alphabet is made up of the symbols for the elements, the absolute fundamental building blocks of, well, everything. And here's the really important part. Each symbol is a letter, and that letter represents one single atom of one specific element. So S isn't just the letter S. It stands for one tiny fundamental piece of sulfur. That's the basic unit of our brand new language. Okay, this is pretty cool. You gotta see how this all started. Back in the early 1800s, a chemist named John Dalton used these little drawings for the elements. I mean, can you imagine trying to write out a chemical reaction using pictures? It would take forever. Thankfully, another chemist, Johannes Jacob Berzelius, came along and basically said, hey, why don't we just use letters? It made the language so much easier to write. And the system he came up with is actually super simple. For carbon, you just use C. Easy. But the letter C was already taken when they got to calcium, so what do? Just use the first 2 letters, Ca. And then you have some odd ones, like sodium being Na. Why? Well, it just comes from its original Latin name, natrium. See? There's a logic to it all. And just like that, you've basically learned the entire alphabet. Okay, so we've got our letters. That's our alphabet. But you can't just throw letters together and hope they make sense, right? You need grammar. You need rules that tell you how the letters can combine to make actual words. And in chemistry, our grammar has a special name. It's called valency. That's it. Valency is simply the combining power of an element. It's the official rule book that every element follows when it connects with another one. It's what makes chemical spelling even possible. Now check out this chart. The easiest way to think about valency is to imagine that every atom has a certain number of hooks it can use to connect with others. An element like sodium has 1 extra electron it's dying to give away. That's its 1 hook, which gives it a positive charge. On the other hand, an element like chlorine is missing 1, so it really wants to grab 1. That's its hook, giving it a negative charge. This chart, it's basically our grammar guide. Okay, this is it, the main event. You've learned the alphabet, the symbols, you've learned the grammar, valency. Now it's time to put it all together and write actual chemical words, or as we call them, formulas. This is where the magic happens. And I'm going to give you a super simple 4-step recipe that works almost every time. Seriously, just follow these steps. First, write down the symbols. Second, put their valencies up on top. Third, you do this little crisscross move. And fourth, you write out the final formula. So, you ready? Let's try it out right now. Let's make something everybody knows, table salt, or sodium chloride. Step 1, symbols. We write down Na and Cl. Step 2, valencies. We put a 1 plus on top of sodium and a 1 minus on top of chlorine. Step 3, criss-cross. The one from sodium zips over to chlorine, and the one from chlorine zips over to sodium. And for our last step, there's a rule that says we just ignore the number 1. So we just push them together and bam, NaCl. You did it. You just wrote your first chemical word. Feeling good? Let's do one more just to make sure it sticks. Calcium chloride. Okay, symbols. Ca and Cl. Valencies. Calcium is 2 plus, chlorine is 1 minus. Now, you know what to do. Crisscross. The 1 from chlorine goes to calcium, and that 2 from calcium goes over to chlorine. We ignore the 1, and what do we get? CaCl2. See that? That little 2 tells us we need 2 chlorines for every 1 calcium. It's like a puzzle, and you just figured it out. You got this. So you are now officially a writer of chemical words. That's huge. But what's the point of knowing words if you can't build sentences, right? Well, these formulas you can now write are the essential parts of something much bigger, chemical equations.
Look at this. This right here is a chemical sentence. It tells a whole story about transformation. In this story, an acid and a base react to create salt and water. And hey, look closely. You can already read some of the words in there, like H2O. Equations like this describe everything, from how a car battery works to how your own body digests food. Your new skill is the key to understanding all of it.
So let's just pull it all together real quick. We started with the letters of our alphabet, the element symbols. Then we learned the grammar, that's valency. And by putting them together with that simple crisscross method, we learned to write words, the chemical formulas that build our entire universe. It really is that simple. You've just unlocked a really powerful skill for understanding the world on a molecular level. This isn't just about passing a test. It's about getting the tools to read the recipe book of reality itself. How cool is that? So my question to you is, now that you can write the words, what chemical story are you going to tell?